Today we're going to begin exploring the technologies associated with spanning tree that we stopped off yesterday in our conversations. So what I'm going to do is I'm going to immediately cut to the whiteboard. Actually, I accidentally cut to the console. The whiteboard is going to be where we need to begin exploring this topic. In fact, let me go ahead and put up some extra room here, where we're talking about spanning tree. Now, spanning tree is a protocol that was created for the sole and express purpose of eliminating the possibility of switching loops or bridging loops in our topology. So irregardless of what term you use. The only thing that I ask you not to use, do not say spanning tree loops. So spanning tree loop it's a bothersome term for me, and 9 times out of 10 it's reflective of someone who really doesn't have an understanding of exactly what it is we're talking about. Now, when this first came out, what was decided was the industry standards body created something called CST, Common Spanning Tree, that was mandated and propagated under a designation of 802.1d. Now, the main goal here was to prevent loops in our infrastructure. Now, whereby those loops could be either between devices that had multiple links connecting them, or if it was between sites that were connected across a layer 2 infrastructure, we wanted to prevent the formation of loops whereby our information could be sent across our infrastructure and then loop back towards us. Now, this is a big danger, and in the early days it was a huge problem, like we were talking about the other day about broadcast storms. Now, a broadcast storm could bring your network to its knees. And when we had this possibility or probability, it was more in the early days of the working with networks. I remember seeing them, and like I said, really and truly all you have to do to be able to troubleshoot it is you begin unplugging ports one at a time until you segment or cut the network off from where the storm is being generated, where that loop is taking place. Why does this happen? It happens because frames, which are referred to as our PDUs at layer 2. That stands for Protocol Data Units at layer 2. These frames have no TTL. There's no time to live value associated with a layer 2 Ethernet frame. Now, that means that they never age out. So they can constantly be looping in our infrastructure forever, theoretically. Now, what we have to recognize here is the basic operation of spanning tree permits us or allows us to bypass this idea of developing loops, because what we do is we hand off control of the layer 2 infrastructure to our protocol, to spanning tree itself. Now, what's going to happen is that we're going to create a loop-free graph. Now, you'll hear me use the word graph all the time. We're going to be talking about loop-free graphs in terms of OSPF. We're going to be talking about our routing protocols and things like that. But a loop-free graph is basically just a logical construction that's going to allow us to be able to mitigate the possibility of developing loops. Now, when we start looking in here, what happens in this scenario? Let's say I had 6 devices. We're going beyond what our lab supports, and everything is interconnected. So we have a full mesh of interconnections here, or as close to it as I can draw without getting all insane. Now, what we have to realize is that we need a mechanism to come in here and start shutting off links. Because what we're going to do is we're going to block traffic on links to prevent traffic from coming back into us. The simplest explanation of this is if I have 2 devices interconnected by the same link, the danger is that traffic can arrive to this switch and then actually be forwarded back out that switch in order to have it come back over here to this device. That means I'm looping the information back. I'm looping back my frame. And that's something that we definitely want to make certain that we avoid. So in order to be able to avoid it, what happens is we hand off control to our spanning tree protocol. And that spanning tree protocol is going to arbitrarily, it's not arbitrary, there's going to be an actual mathematical process. But right now, let's look at it just from the point of view of an arbitrary decision, terminate any possible links that we may have that can lead back to the destination. Now, again, this is in its quote-unquote simplest form. Now, over here, we've got a much larger scenario where what we need to do is we need to make a determination as to what devices we're going to use to be able to achieve reachability in our infrastructure while creating this notion of a graph. Now, when we're done, what we're going to do is I'm going to say this is going to be A, B, C, D, E, and F. And you see we have scads of interconnections between these devices. But what we want to pay attention to here is that in all actual fact, what we're going to do is we're going to run a process selection where we create a root bridge. The root bridge is going to act as the root of our tree. That's where the term comes from. We'll talk about how that happens shortly. But once we elect a root bridge, now what we're going to do is actually compute this graph that I've been talking about. So when we look at this, I'm going to go ahead and erase some of this. What we're going to find is I'm going to erase my example because I want to talk about this idea of the graph. So I'll pick a black pen. We'll just start from scratch. And what we'll do is I'm going to say A is my root. Now what I'm going to do is I'm going to create a tree. A tree has branches. And what we're going to do is we're going to use a computation based on cost. So what I'm going to do is just arbitrarily assign each one of these links a cost of 1. So every link in this infrastructure has a cost of 1. So they're all treated equal. So what we were going to do is we're going to pick the path that has the least cost in order to obtain connectivity to this root bridge. Because that's exactly what this is. This is the root bridge, A. So in other words, B has a connection. Now if I look at it from the point of view of logic, B can go directly through this link at a cost of 1. Or it could use a summation of different loops that are still going to cost more than 1. So what it's going to do is it's going to take these links that we're talking about, all of these other links that it's got connected, it should actually have one going all the way down here, and it's going to terminate those links. It's just going to put them in a blocking state. So we're not going to allow control plane processes or forwarded information to run across them. So what will happen is this is going to be one part of my graph. Now if every device has a single link going up to A, what this is going to look like at the end of the day is going to be something like this. I'm going to have C, I'm going to have E, I'm going to have F. So it's 1, 2, 3, 4, 5, and I've got E, F, B, A, B, C, I need D. D. So let me get my big head out of the way. What we recognize right here now is that we have a graph. That's what this is. This is a computational graph that we have created. Now, if these are the only links in our infrastructure that are forwarding traffic, it is absolutely impossible for us to generate a loop because everything to reach any particular component must go through the root. Now, when we look at this and we start going through and start making the configuration, what we're going to have is that we can manipulate this election or we can let this election happen on its own. If we let the election transpire on its own, what we're going to end up having here is the device with the lowest MAC address is going to become the root of our spanning tree bridge or our spanning tree topology. Now that means specifically that older devices more often than not would trump our baseline configuration. Now if we want to be able to manipulate that, what we're going to do is we have the capability of changing or manipulating priority. The priority adjustment allows me to go in and say I'm going to set a value, and again, lower is better, such that I can designate which device is going to be the bridge in my topology. Now, a lot of people here don't like this idea. They don't like this idea because, like I said, if you have a crappy Calpana, and a lot of you guys probably don't even know what a Calpana switch is. I'm sure William probably does. But if you've got a Wellfleet or a Nortel or a Bay Network switch or an old crappy Calpana switch somewhere in your infrastructure, and you take it and plug it into your high-speed 3560 and newer configurations that you have running in your topology, and 3560s are old, by the way. But the main idea here is what's going to end up happening? It's going to become the root bridge. Almost 90% certain if we've left all of our priorities to the default. Now, the issue here is that what we have to recognize is like I said, or I've mentioned in the past, there was a long-standing war, and it's the only way that I can really describe it. There was a war, and there was a war between Cisco and the standards body. Now, this war was about one thing and one thing only: VLANs. So when the industry standards body came out and created 802.1d for bridging, Cisco looked at this and said, that's a great idea. We like that because we got a whole plethora of stuff out of here. Because 802.1d gave us 802.1p, which actually gave us 802.1q. This is where trunks came into existence. Trunks, let me go ahead and change pins here. Trunks transport multiple VLANs. Now, Cisco latched on that and they said, well, that's really, really cool, but the whole idea here is that this entire group constituted something called common spanning tree, which means there was no idea of VLANs. There was no construct of VLANs. And like I said, keep in mind that everything was based on MAC address and priority. Now, when we look at how this is all sliced out, Cisco said, well, we like this. This is a really good idea. We love this idea of trunks, because this gives us the capability of being able to do something that we've been wanting to do. We want to implement this concept of VLANs. Now, Cisco came up and said, well, our devices need to be able to support anywhere from 1 to 4,094. The actual number is 4,096, but some of those are reserved. VLANs. Now, does that mean that our switches can actually support that many VLANs simultaneously? The majority of the switches that we have, the 3560s, the 3550s that we explore and work with in the confines of the lab, what we find out here is that we can really support about 1,000 VLANs simultaneously. But that's not an iOS limitation. That's a memory limitation. So remember, we have to have that CAM table, that content addressable memory table, and that content addressable memory table utilizes RAM for every entry. So when we take a look at the fact that many of our devices have limited amounts of computational RAM, what ends up happening is we basically have to cut back on the things that we can actually keep in these tables. So what we'll find is there's actually a limit to the majority of the devices with regard to all of the devices, with regard to how large our content addressable memory is. So in other words, they can only memorize or know or learn so many MAC addresses simultaneously. Now when we have a full table, what ends up happening is we flood information everywhere and try to make sure that we do discovery through the concept of ARP for every piece of traffic that we have, especially if it's not in the table. Now there is a hack where we can go in and you can use a program. I think MacOff is one of the best ones, where you can go in and you can just pelt your servers with MAC addresses using a Linux server that just constantly registers MAC addresses until ultimately you fill up the table. The moment we fill up the table, the system is going to go to flood operations, which means it's going to be sending an unknown unicast frame out, try to find out who is what. Now, if the database, if the CAM table is full of bogus MAC addresses, even the MAC addresses that are legitimate on our infrastructure are going to be forwarded. This gives us a capability if we're going to be looking at something with regard to I don't like the term cyber attacker, but if we're going to be trying to leverage the network, now what we can do is we can use a sniffer and we can start capturing information about everything because it's being flooded. It's being flooded to broadcast destination addresses. So in other words, anybody can see the information provided they have a sniffer plugged into the infrastructure. Now, when we look at this idea of common spanning tree only supported the notion of a single VLAN, what Cisco calls a VLAN. So it would be the equivalent of VLAN 1. But common means there's one instance of spanning tree and that's it. In Cisco's deployment, they said, well, we really like this idea, 802.1d, but what they did is they created PVST and then later migrated it to PVST+. Now, PVST and PVST stands for per VLAN spanning tree. Now, what Cisco did was they came up and they said, well, here's the deal. We support 1 to 4,094 VLANs. And what we're going to do is we're going to do that by having a spanning tree instance for each VLAN. Now, that means if I have 1,000 VLANs, that means I'm going to have 1,000 instances of spanning tree protocol. Now, that begs an issue, because if we support VLANs, does that mean that we can't communicate to a device that's running 802.1d? And a lot of people are going to tell you that 802.1d is not supported by Cisco, and that's simply not true. 802.1d is going to be the standard that's going to be running on our routers when we configure our routers to act as switches or to do something called bridging. And it's going to be an ideal opportunity for us to take a look at this. So what I'm going to do is I'm going to cut over here and I'm going to go to, first let me center this a little bit. I'm going to actually go to a router, something we haven't done yet in the class pretty much. But I want to bring up a router. So I'm going to cut over and I'm going to go to R2 in my topology. And right now we've got nothing on here, so I just want to put my base config just so that we don't have to wrestle with anything. So config T, no service, timestamp, no IP domain lookup, line console 0, logging synchronous, no exec timeout. No. And lastly, our host name, which is going to be R2. Now what I want to do is I want to configure this switch, this router, because if I come up here and say end, and I'll go ahead and write this so it doesn't go anywhere for me. It's going to overwrite my previous configuration. Now when I look at this, and I do show spanning tree, notice it says no instance of spanning tree exists. That's because it's a router, it's not a switch. I told you, we switch between interfaces, but I do not have the capability right now of being able to operate in the context of a spanning tree environment. But I want to change that. So what I'm going to do is I'm going to come up here and I'm going to say bridge, and I'm going to tell it what I want to do. I'm going to actually say bridge group 1, and then I'm going to come in here and I'm going to tell it what I want it to be able to do. Well, I want it to run a bridging protocol, so I'm going to tell it protocol. Now the moment that I have my protocol, now I need to, and I'll just do shift question mark, and now what ends up happening here is that I need to pick, do I want to run DECNEC switching protocol? Do I want to run an IBM switching protocol? Do I want to run the industry standard 802.1 series routing bridging protocol? And that's exactly what I want to do. I'm going to come up here and say IEEE. Now let's see what happens. If I do show spanning tree, notice now I'm actually running spanning tree. It's not assigned to any interface, but my system is generating spanning tree information, control plane information, and guess what? It's using common spanning tree to do that. It's using CST. So it's actually running 802.1d, and here's how we know. Notice right now, in this particular area, I have my bridge identifier. My bridge has a priority of 32768. 802.1d mandated and specified a 32768 when Cisco implemented it. That's what Cisco uses as their default priority. So whether we're running per VLAN spanning tree or whether or not we're running an instance of CST on a router, we're still going to always pick the same default priority, 32768. Now when we also look at this, we also have our MAC address. Now what I want you to see here is we have a hello timer of 2 seconds. We have a max age timer of 20 seconds. And what we need to do is we need to talk about that because we haven't talked about modes. In the confines of 802.1d, we have what's referred to as a 20-minute blocking timer. We have what's also called our delay or our forward delay. Our forward delay is 15 seconds by default. But what happens here is that we have two states. We have a listening state and we have a learning state. What will happen is we're going to take this value at 15 seconds and it's going to be what we use as our timer for each of these two states. So what we're going to be doing now is we're going to be listening. What are we listening for? We're listening for a logical construct called a BPDU, a Bridge Protocol Data Unit. Now the Bridge Protocol Data Unit is used for the purpose of initially electing that root bridge that we talked about. And remember, I told you at the top of the graph we'll have the root, and that's exactly what we're going to do. The criteria for root election is going to be either the lowest priority or the lowest MAC address. Now we were talking about that crappy old Calpana. You go throw it into your infrastructure and all of a sudden it becomes the root bridge of your environment. That's not really smart. All right, but we've also got the reverse of the problem. Let's say I've been running my layer 2 environment for years, everything is stable, and we've just added an office or we've added a new floor in the building. I go on out to CDW or go to whoever my vendor is for my Cisco equipment and order a brand spanking new switch. And we get that switch, that 3750 or whatever, and we take it and we plug it into our infrastructure, and it's going to, what would happen if it had the ability to be able to just assume the role of the root bridge without any base configuration? So what Cisco was trying to do is this implementation meant that the ability or the act of adding a new switch was designed not to overwrite my existing layer 2 environment. Now, in an ideal and perfect world, would I want that brand new switch to be in charge if it's got more memory and more capability and everything? The answer to that question is the answer that we always have. It depends. Is it going to disrupt your environment? The moment you plug it in, is it going to cause your layer 2 environment to reconverge? Remember, a reconverging infrastructure is not going to forward traffic. Now, and that's why, just like William's saying here, that we always make certain that we assign our priority. Never, ever, ever, ever allow the root bridge election to take place on its own in your infrastructure, because it's one of those things that can change over time. And the idea also here is that William's suggesting the fact that when we do elect our root bridge, we want to make certain it is as central to our environment. One of the things we'll talk about is a concept called diameter. Diameter allows me to constrain my BPDU traffic. Now, the problem with that is that in many implementations, the root bridge is not necessarily, or we don't necessarily have a device that's sitting smack dab in our environment. So you're going to have to use your judgment. But yes, I do agree that what we want to do is we want to have it as centralized as possible. The reason being is we want to have as many individual links coming back to it as possible, and we also do not want to run into a scenario where we're daisy chaining a series of switches unless we can possibly avoid it. So in other words, a single home between all the switches would be the operational parameter in an ideal and perfect world. Now, looking at this, like I said, we're currently running this process. The other thing that we have is this idea of the max age. So we have a 20-second max age time. So here's the situation. If I learn information via a BPDU, and I enter it, and I start doing my computation, I'm going to keep that information in my table, in my bridge computations, for a maximum of 20 seconds. If I do not receive a subsequent piece of information that shows me my control plane is operating, what's going to end up happening is when this max age actually expires, I'm going to recompute my layer 2 environment, because this is an ideal way for me to determine whether or not I've lost a neighbor. But the problem is these timers are horrendous. I mean, if we take this and add it up, so from the time I bring a switch up and make it operational, I have 20 seconds of blocking. There's nothing that I can do to change that, and it's going to do it every time from a scratch start. Now, once the switch is up and running, it'll never go back through this until I bring the switch down and bring it back up again. Now, when we go through this, what's going to end up happening is that means from a scratch start, I have 50 seconds. That's an eternity, especially when you got things like voice in your infrastructure, telephones. That's on power up. If the switch is already initialized, I have a maximum of about 30 seconds. Now, a lot of people think that if I change the max age, I'm going to be able to speed this up, and that's not true. All I'm going to do is I'm going to detect the problem faster, I'm going to reconverge, but I'm still going to have to step my forwarding delays. Now, we can go in and change the forwarding delays, and you'll be doing that in the next series of labs that you're going to be doing. And I mean, it's not overly difficult, but the main thing here is that this is common spanning tree. And what ends up happening is we create that idea of the BPDU, which carries another logical construct for us called a bid. BID. The bid is going to be the bridge ID information associated with each of our devices. As we can see here, it's 32768 and my MAC address, 00A:B82D.ca88. These two values put together become my bid. The lowest MAC address, or actually the lowest priority, will automatically trump everything else. In the event of a priority tie, the MAC address is allowed to break the tie. Now, this is common spanning tree, but common spanning tree does not run on Cisco switches. Cisco uses their own solution, which is what we were describing earlier, and that's going to be the idea of per VLAN spanning tree. So the moment I create a VLAN, let's say I create 10 VLANs in this scenario. So I create 10 VLANs. Those VLANs can be 10 to 19, or 10 to 20, however we set them up. So those 10 VLANs, or these VLANs that we just created, now are going to have associated with them an instance of spanning tree protocol. And that's why it's called per VLAN spanning tree protocol. So per VLAN spanning tree protocol plus. Now the question that I have to pose here is well, if that's the case, let's say I have 4 colors here that I can work with. Let's say we have VLAN 10, VLAN 20, VLAN 30, and VLAN 40. All right. Now when I look at this, I've got VLAN 10 traffic. I've got VLAN 20 traffic. I have 30s traffic. And then lastly, I have 40s traffic. I'll refrain from using yellow when and where possible. So now the issue is that we have this logical construct that we were talking about called a trunk. Probably should have done that in black. So this is my trunk. Now what ends up happening here is through the use of this idea of 802.1q, which is a trunking encapsulation, what I'm going to do is I'm going to create a stream of traffic that's going to be comprised of individual frames representative of each of these individual VLANs, and it's going to reproduce, it's going to actually be replicated. So now what ends up happening is we can quite easily see that I'm able to move all of these VLANs, 10, 20, 30, and 40, across this trunk, and I can do it because what happens is my 802.1q gives me the capability of inserting information into each of these individual frames that are saying I'm part of, in this instance, VLAN 10. In this instance, I'm part of VLAN 20. In this instance, I'm part of VLAN 30. Now, once it arrives on the other end, all that VLAN information, all of this trunking information, the VLAN header, any of the flags or tags or whatever it is we want to talk about or call it, gets popped off. So it's going to arrive and it's going to be processed as individual traffic based on its individual destination, but it's still going to be on the system kept in its same VLAN. So this allows me to make certain that VLAN 10's traffic is not going to contend or contest with VLAN 20. But the problem here is that these trunks are going to be running multiple VLANs, and if I have an arrangement whereby, remember, common spanning tree said that my priority and my MAC gave me my bid, my bridge ID. Now, PDEs are used for other things other than just this root bridge election, and we'll get into that. But what we're going to end up happening here, what we're going to find is that in this particular scenario, how do I make certain that I can have VLAN 10 and VLAN 20 separate? Because if I go to my system and I type in my configuration, actually I need to go to a, let me remove this bridge. Config T. No bridge 1 protocol IEEE. And we'll revisit this. This isn't in the context of the lab. I'm just giving you a frame of reference. And also, this command right here is a crap ton of help when it comes to troubleshooting configurations and playing around when you're trying to learn. And I'll show you how we do that. But let's go over to SW1, or Cat1, excuse me. Config T, do my basic configuration, en config T, no IP domain lookup. Line console 0, logging synchronous, no exec timeout. Exit host name, Cat1. All right, so we got the basics in here. Now, what I want to look at here is a spanning tree. I'm going to type show spanning tree and just press enter. And what this is going to do, it's going to give me information about the VLANs that I currently have running. We can see, and I'll just put this behind my head since I'm tired of reaching over and grabbing it. Show VLAN brief. The only VLAN that we have configured on this device is the VLAN 1 that we have up and operational. We're not using any of these reserve VLANs that we were talking about. So every time I look at my switch, I'm going to see only information associated with one VLAN. Show spanning tree, hit enter, and notice it only gives me information associated with this idea of VLAN 1. It says VLAN 1 right here. And what we see here is all of the ports that I have are on my device that are actually up and operational, or at least enabled. All of them are running information associated to that particular VLAN. Now, when I look at this, what I'm really looking at is the fact that if I come in here and create another VLAN, config T, and I create VLAN 10, I just made another VLAN. So if I come up and say show spanning tree and hit enter, notice I see information for VLAN 1 and VLAN 1 only. Let me grab my mouse here. I got papers in front of my mouse. The only thing that's giving me information, again, is VLAN 1. Now the reason that that's happening is that we do not have VLAN 1 assigned to an interface. So if I come through here and I say show the spanning tree, and I select it specifically to say VLAN 1, it's going to give me information. If I say VLAN 10, it's going to tell me that there's no instance of spanning tree running. But Terry, I thought you said that if I had VLANs, I was going to have an instance of spanning tree on the VLAN. You are, provided that VLAN is participating on an interface. So I could come over here to an individual connection and say config T interface FAO 17, actually I need to use 18, and say switch port mode access, switch port access VLAN 10. Now I'll come up here and do show interface FAO 18 switch port. And what we're going to see now is VLAN 10 is actually running on this interface. And since VLAN 10 has been assigned to an interface, do show spanning tree for VLAN 10, we're going to see the fact that it's not up and operational. Now, I thought you said, Terry, that if we assigned it to an interface, it was going to be up and running. Well, let's take a look at that. Show interface brief. Do show interface brief. Do show IP interface brief. We put it on FAO1. No, we put it on 18. Down. So let's change it. Let's go ahead and remove that configuration so don't forget about it. Now if that link was up and operational, it would be working. So I'm just going to say default interface FAO 18 and take it back to factory configuration. So do show run interface FAO 18 should show me that I have my regular default config here. So what we're going to do here is since this interface is down and it's not operational, it didn't bring the VLAN up. The VLAN is not operational unless it's working on a trunk. So it's not sufficient, or a trunk or an access port. It's not sufficient just to assign it. It has to be in an operational state. In other words, we have to have the ability to forward before spanning trees are even going to come into play. So when we go through here, what we're going to do is I'm going to set it up on a trunk. So show CDP neighbors. Let's take a look and see what we have here. We have our connection. Just for clarity's sake, I'm going to go in here and just go ahead and assign host names. I'm not going to do anything else. EN, config T, host name, cat2. We're going to say here EN, config T, host name cat3. And lastly here, EN, config T, host name, cat4. All right, let's go back over to cat1 now. Now in the confines here, remember we got that timer, that hold down time. You can see that right here in the second column. Oh, my fingers. The second column over here, or the third column where it says the hold down time. That's going to be how long it's going to take us for us to set everything up. Or I could simply come in here and say clear CDP table. Hit enter. Show CDP neighbors. First I'll have nothing. CDP neighbors. And then what will happen is as soon as the hellos start bouncing back and forth, everything will come up and I should have all of my connectivity to all of my remote devices. Gotta wait for it. See, sometimes clearing these tables isn't quite the efficiency that you're going to hope for. We'll go ahead and let this keep percolating. I'll go ahead and make my changes now while I'm able. So config T, all I want to do is I'm going to create a trunk. So I'm going to force it. I'm going to come in here and I'm going to say interface range FA0 19 to 24 switch port trunk incap.1q switch port mode. Actually, we'll say switch port mode dynamic desirable. We'll force it and we'll use the dynamic methods to do it. No shut, just in case. Exit. Show CDP neighbors. We should have our neighbors by now, which we do. We got 2 for each of our individual switches. And now if I come up here and say show spanning tree VLAN 20 or VLAN 10, what we'll see is I'm going to have information. But look where the spanning tree says it's running. It's running on every one of these interfaces. And right now it's learning. Still learning. Let's see if I can catch it between learning and listening. Okay, it skipped learning and went right straight to forwarding. Now everything's forwarding. Now when we look at this, we can make an assumption here. Because when we go through and we start looking at this, we could have adjusted the timers on CDP. I just tried, right now I'm not messing with stuff. You guys are going to play around with different things in your labs. William's suggesting why we don't just change the timers on CDP. I'm trying to illustrate the fact that if in the lab, if they don't tell you to adjust the timer on CDP, you leave that timer alone. And if you're going to leave it alone, then you're going to have to get used to working with the issues that the CDP is going to cause. So, I'm a firm believer in if you're going to race a marathon, you need to train by running a marathon. So if you're going to be working in the environment and Cisco doesn't tell you to change something, do not arbitrarily just change something on your own. They say no extra configuration is going to hurt you, but what if you make a mistake? Or what if there's a configurational hang-up or a glitch? What you want to do is you want to stay with the baseline operational parameters when and where possible if Cisco allows you to be able to do that. All right, so that's why I stay away from going in and manipulating the timers. So when we look at this, there's an assertion here. Now remember our previous conversation. I said we elect a root bridge. Well, there's two things on this that tells me that Cat 1 is my root bridge. First and foremost is this one right here. I mean, that's hard to miss. This bridge is root. Now the other part of this is that we also notice that every one of our interfaces are forwarding, and they're in what's referred to as the designated role. What is a designated port? Well, a designated port is any port that leads away from the root bridge. So a root bridge, all of its ports lead away from it, so they're obviously going to be all designated. So anytime you do an output command and you see all of your interfaces and everything is designated, forwarding, even if they do not show you anything from here up, hint, 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 you may, or you can tell that this is going to be the root bridge because every port is going to be in designated forwarding. And the root bridge is the only switch that's going to have every port in designated and forwarding. See, William, different VLANs can have different roots in the same spanning tree domain. I'm getting ready to go through that. That's the whole issue here because there's some additional information here. Because remember I said that in common spanning tree, the BID, the bridge ID that was generated was the priority and the MAC address. Well, the issue here is that this is for, they have no idea of VLAN, so assigning this value is problematic for us. Now what Cisco ended up doing is they basically hacked the process. Because what you're going to see here is in the output of this show command is what they did. Look right here. We have a priority. We have the MAC address. So we have all of the piece parts and components necessary in order to be able to support this idea of priority and MAC address. But Cisco also came out with something called the System Extended ID. Now the System Extended ID is nothing but the MAC address. But the VLAN. So what they've done is if I have 4098 or 94 VLANs, all I'm going to do is I'm going to take my priority and I'm going to add my VLAN to it. So in this instance, notice my priority is still 32768 by default, but I take 10 and add to it, and that's going to produce a priority of 32778. That's how we maintain the different instances for spanning tree, because for every instance of spanning tree, we're going to send a BPDU associated with that VLAN. So it's going to be, there's going to be BPDU sent out for VLAN 10. There's going to be BPDU sent out for VLAN 1 in this instance. If we do not have a functional interface, then we're going to stop sending information for that particular VLAN. The idea here is that on an access port, move my head out of the way, on an access interface, if I have a VLAN assigned, obviously spanning tree is going to run on that VLAN, on that interface. But that interface must be in up state. That was our problem. We were in down. We didn't go anywhere. Or we can have it on a trunk. A trunk is going to have every VLAN by default configured, 1 through 4094. Now, when we start looking at this, it's through the exchange of information that we elect this root bridge. So what's going to happen is all these values, if the priority is the same, which remember, in VLAN 10, every priority is going to be the same for every device unless we go in and we manipulate this process. All they're doing is taking the default of 32.768, adding the VLAN to it, and using that for our computation. Now, what I could do is I could go in here to any other device. Let's just pick Cat4, for instance, since Cat4 lends itself so well to our work. I'm going to move over to Cat4, and I want Cat4 to be the root bridge. But let's draw our topology first. All right, so let me come in here. I'll grab my black pen. We have Cat1. We have Cat2. We have Cat3. Actually, this would be Cat4. This one would be Cat3. And right now, the graph looks like this, irregardless of how many interfaces or links that we have. Now, I'm on Cat4, so we're on this switch right here. What I'm going to do is I'm going to take myself completely out of the equation, and I'm going to execute the show information, show spanning tree, and show spanning tree for VLAN 10. Now, notice we don't have a VLAN instance. But do we have a trunk? Show interface trunk. Yes, we do. We have a trunk. Where does that trunk go? Where does 19 and 20 go? Show CDP neighbors. It goes, well, we've got connection to 1. Here we have connection to 3. Here we have connection to 2. So on this switch, what I'm going to do is I'm going to change that behavior. I'm going to shut down all of my interfaces except those going to 1, just so that we can capture everything. So config T, interface range, FA0, 19 to 20. I'm sorry, it should be 22 to 24. Shut, show interface trunk. There we go. Show CDP neighbors. Do show. Now we only have, let's see, 21 still up. Shut. Do show CDP neighbors. Now we've got what I want. Now when we look at this, I can come up here and type show spanning tree for VLAN 10, and I'm not going to see anything. Show interface trunk. And the reason that we don't see anything, show interface trunk, is the fact that we don't have a VLAN here. Remember, we only have VLAN 1. So in order for this to automatically be able to work, I need to create the VLAN 10 here. Config T, VLAN 10. Exit. Show interface trunk. What we're going to see here is now we have VLANs 1 and 10. So if I come up and they say show spanning tree VLAN 10, what happens here? Notice this switch just became the root bridge. So Cat4 is now the root. Let's take a look at that. So Cat4 is the root. The root bridge has a value of 32.778, and it has a MAC address of 019.0606.7180. And it was elected the root. Now let's take a look up here at Cat1. Do the exact same output here. Notice we have here, I'll do it in a different color. I'll do it in red. Here on Cat1, we have 32.778 matches. And we have a MAC address of 0.19.060C5E80. So matches, matches. Notice 6 is less than C, so this becomes the root bridge. Now, this still says that this is the root bridge, but if I refresh this output, what we'll find is it now says the other bridge is the root bridge. So notice now it says the root bridge is whatever bridge that has the MAC address of last 47180, which is this bridge right here. Now what happens is by logical, by construct here, this bid is lower. So this is a lower bid because it has a lower MAC address than this one. So this one's higher. Now what I want to do is I want 1 to be the root bridge. And here's why. Because right now if traffic is going to travel in this infrastructure, it's going to have to travel this way and go back out to get over here. That's not something that I want to have happen in my infrastructure. So what we're going to do is I'm going to eliminate that problem by making Cat1 the root bridge. Now I have 2 ways that I can do this. I'm going to do this first of all and illustrate it using what I'm going to refer to as the priority manipulation. Actually what Cisco calls the priority manipulation. So I come in here and I say spanning tree for VLAN 1 or 10, excuse me. And what I want to do is I want to affect its priority. But before we do that, let's take a look at some of the other options that we have. There's that forward time. That's how long we're going to sit in listening and learning. The hello time, how often we're going to send out our BPDUs. That max age, how long we're going to wait before we receive a BPDU before we freak out. We have priority and we have root. These are the 2 elements that I want to talk about right now. So what I'm going to do is I'm going to come over here and I'm going to say I want to make a priority, but notice here when I use the question mark, it tells me I have to enter it in increments of 4096. All this does is ensure I have spacing between my VLANs. So my numeric values can't be the same. So I can't accidentally have VLAN 10, which is supposed to have a 32778. I can't have VLAN 20 accidentally have a 32778 because 32778 belongs only to VLAN 10. So my increment of spacing has to be maintained. Now if I want this to become the root bridge, what I'm going to do is I'm going to pick one here and actually I always hate it when I have to do this. What I'll do is I'll configure this and I'll set it up as a double. So I'm not going to use 0. I'm not going to use, that's what we'll do. We'll say 4096. I'll just pick the first increment. Now, what happens if I come up here and I said 3? Notice it's going to give me the values that I can enter legitimately. Pretty handy tool. In fact, what I'm going to do is I'm going to change this. I'm going to select the priority of 8192. Now here's the situation, see? What we did is we did this specifically for VLAN 10. So if I come up here and say show spanning tree for VLAN 10, what we're going to see now is that we're the root bridge now. So Cat1 took over. Why? Because Cat1 has the lower priority. Now we have our 8192 with our system extended ID of 10 adding up to 8202. But if I come up here and look at VLAN 1, what we're going to find out here is that when we look at VLAN 1, notice our root bridge. So the root bridge is this one right here, which is 5B00. So where the heck is 5B00? I mean, the other switch was 7180. What I'm trying to illustrate here is the fact that our root bridge, our secondary devices, all exist on a VLAN by VLAN basis. That's the whole benefit of having this idea that Cisco come up with VLANs and instances of spanning tree per VLAN. Because in the scenario where Cat1 is going to be the root bridge for every VLAN, it could be a bottleneck. I may have another switch, like for instance, if I have my infrastructure that's cross-connected here, my infrastructure was like this, I could say I want Cat1 to be the root bridge for VLANs 1 through 10, and I could have Cat2 be the root bridge for VLANs 1 through 10 and for 11 through 21 or 20. So the idea is it gives me the fact or the benefit here of being able to pick which one of these are going to be the root for which VLANs. So again, administrative load balancing. Now, it's hard to keep track of sometimes, and you have to learn how to read these tables. And Cisco's definitely going to hit you with this in the confines of both the config section and on the troubleshooting section, because you will have a layer 2 troubleshooting component. Now, one of the things that we mentioned here is William's talking about cost. Now, I want to talk about cost, but first I want to cover the other method of electing a root bridge. So if I slip past it, William, remind me, all right? Because we have the capability of changing the way we actually do our cost computations. What you're going to see here is these values are default configurations that are part of PVST+. Now PVST Plus uses, or is old, and remember, back in the day, a 100 megabit connection was considered blindingly fast. So the idea is that we have these algorithms that run against our bandwidth that allow us to compute cost. All right, so what happens is this method, the default method, is now referred to as what we call the short method. We have a capability of doing this where we're long, where we're going to see values of like 20,000 in here. Now the rationale behind this is I have 1 gigabit, 10 gigabit, 40 gigabit, 100 megabit Ethernet's coming. So what we wanted to do is we wanted to have an algorithm that was going to very clearly delineate between each of those different types of links. Because what happens is the faster you go, after you go above 1 gig, the short method doesn't really compute the difference between a 1 gigabit interface and a 10 gigabit interface. All right? So as we go through and we start looking at how all of this is going to be interconnected, I want to change this election. I actually want Cat1, and I'm going to go ahead and just move all of this off of the screen here. I want Cat1 to be the root bridge for VLAN 1. So how do I do that? Well, I don't want to use the priority command. I want to show you the other method that I have here. So when we come up and we look at this and I say show, we already did that, config T, all I'm going to do is I'm going to say spanning tree, and I'm going to come up here and I'm going to say for VLAN 1, I want to use what I call a one-time running macro. Now this one-time running macro is going to take a look at all of the bit information, all the BPDUs that we've been receiving, and it's going to do a mathematical computation to this local switch, and the switch is going to assert itself as the root bridge using the minimum amount of manipulations possible. So here's the deal. So I'm going to come in here and I'm going to say spanning tree 1, root, and I'm going to say primary. So I want to be the primary root bridge for the configuration that I have such that I'm going to be in charge of VLAN 1 now. So if I come up now and say do show spanning tree for VLAN 1, what I'm going to see is I am now the root. Now how am I the root? Well, I came over here and I did a priority manipulation. I am now 24,577, not 32,768 plus 1. So it should have, or originally, it would have been 32,769 since it was VLAN 1. So I took 32,768, added 1 to it, and came up with this value here. Now, what this tells me is that I'm now going to be the root bridge for VLAN 1, which I can see. And I don't know which bridge was the root bridge for it before. But what I'm going to do is I'm going to run another computation. I've changed my mind. I'm going to go over to Cat4, and I want Cat4 to be in charge. Now, when I come up here, is I'm going to say config T, spanning tree, for VLAN 1, root, primary, and I'm going to execute that command, do show, spanning tree, VLAN 10, VLAN 1. And I'm going to see now I'm the root. And notice my priority is 4277. Well, what did we say it was on Cat 1? It was 42577. I went to Cat 4 and now I've got 42577. So as we go in and we start looking at this, the whole issue is the fact that I match priorities. So typing this command with regard to the root primary, what ended up happening was all I did is I matched my priority. Why? Because my MAC address was already lower. All right. So now the thing is the question here was actually say, can we do a root guard to prevent other switches from taking over as root? Yes, but that's going to put us in root inconsistent state on a given VLAN. If we do that, and we'll be talking about these options a little bit sooner or a little bit later, what will end up happening is we won't be forwarding traffic on that link for a given spanning tree instance or a given VLAN instance. So you got to be careful with root guard. Root guard prevents something from being able to assert the role, sending what's referred to as a priority or a superior BPDU, which means it's got a lower BPDU than the current root bridge. We can stop that process, but what it's going to do is it's going to take that port for that VLAN and put it in root inconsistent state, which means we're not going to be forwarding traffic across it until such time that we satisfy eliminating the idea of having the superior BPDU. But once you've got your layer 2 environment, doggone right, go ahead and you want to iron it up if you're going to be running spanning tree or per VLAN spanning tree plus. Now, most instances or most places that I work with, I either run rapid per VLAN spanning tree or MST, which we're going to be talking about shortly. But the main thing here is understanding what's happening in this process. So when I bring up my devices, let's say I have Cat 1, I have Cat 2, and I have Cat 3. We're just going to put them in a triangle. Now, what's going to happen is if I come up here and I say that Cat 1 is going to be the root bridge, we already know all of its ports are going to be designated. We also know that they're going to be forwarding. They're going to be sending packets. Now, what's going to happen is Cat 1, 2, and Cat 3 are going to start looking at their links. So this link versus this link. And what they're going to do is they're going to run a computational cost. So we'll come up and say, in this instance, we're going to have a cost value. Let's say it's 19. So for this switch to reach the root, if all of our interfaces are equal, that means it would be this way, 38, or this way at 19. So it's going to pick this port, and this port is going to be called a R port, or a root port. What is a root port? A root port is a port connected to the root bridge, or leading towards the root bridge. So that means this is going to be a root port, and it will be forwarding. Root port, forwarding, because 19 is less than 19 plus 19. Now what we need to do is we need to take a look at this link right here. Well, first we look at it from the point of view, well, what's going to happen here? Well, would I ever send information to this device to reach the root? Because it's connected here, right? No, we would never do that. So what we're going to do is this is where spanning tree is going to come in here, and it's going to put one of our connections into blocking state. Blocking state is a port that is administratively blocking BPDUs as they receive on our environment. Now, this is obviously describing, as William's pointing out, a working scenario. The moment that I lose a link, so if in this scenario right here, I were to lose this link right here, what will end up happening is my layer 2 environment will reconverge, and I will actually begin using this link, but I will not be able to use this link because obviously it's down. But what's going to happen here is one of these ports is going to be designated as forwarding, the other one is going to be blocking. Now, the reason that we do this, why is one end of the link forwarding even though the other end is blocking? Why aren't they both blocking? Well, we want to be able to continue to receive information associated with what's called a TCN. A TCN stands for a topology change notification. So let's go back to the big whiteboard and let's talk about that. So in a scenario where I have Cat 1, Cat 2, and Cat 3, like we illustrated before, and we're connected, and Cat 1 is the root bridge, so this means we are designated, and forwarding, That means these are root ports, assuming that our cost is 19 on all of our links. And what we're going to do here is what happens when this link right here, well, let's see, let's go ahead and add another router down here. Let's say Cat 4. What happens when this link drops or dies? Well, what we need to understand here is after we have elected the root bridge, in PVST+, we have an issue here. And that issue is that only the root bridge is going to be able to indicate that there's going to be changes in the topology. So here's what happens. This link goes down. Well, that means this switch is going to send a message out of its ports saying, something's happened, I've lost this connection right here. Well, this message would be relayed through our infrastructure until ultimately it reaches the root bridge. Now, if it was to go up to Cat 2 would end up forwarding it to the root bridge, and it's going to send a message back, and that message is going to say, it's been sent, you need to wait, stop sending me this message. Now, once this message arrives at the root bridge, what's going to end up happening here is that this is going to go through and it's going to do a TCN, a topology change notification. So in other words, this message, which is just a special BPDU, gets sent to all of the devices by the root bridge, and what they do is they actually reconverge on the new topology. Now in this instance it's a single link, so it's not really going to cause us any problems. But if this was a transit link, then what would end up happening is for the duration of our reconvergence, our layer 2 environment would not be forwarding information. But we've been calling attention to this idea of our link speeds. Now what will end up happening is if I want to manipulate the link speed, I have two ways of doing it. I can assign a cost, or I can change its configured bandwidth. Altering its configured bandwidth is going to change its assigned spanning tree cost. But the problem is as we were talking about, using what we call the short method, we do not have the capability of being very granular. Why? Because our numeric ranges get closer and closer together. I would rather a 10 gigabit or a 1 gigabit connection look radically different compared to, say, a 100 megabit connection. Let's cut back over to the gear and let's take a look at what I'm talking about. Let me bump this just a little bit. Every time I hit it, I seem to drag it to the left a little bit. So looking at this, what we see here is notice my cost values. Do show spanning tree. For VLAN 10. I want to be the root, so we'll use VLAN 1. All right, we are the root. So notice this cost, VLAN 19. Or I'm sorry, cost of 19. Well, one of the things that I could do to alter this is I could go over to interface FAO 19, and what I'm going to do is I'm going to change the bandwidth. So let's say my bandwidth is now going to be 1,000 kilobits. Now let's take a look at it. Do show spanning tree VLAN 1. Look what happened here. My cost went up. It's not 19 anymore. So let's look at this again. So what happens if I change the value even further? Let's go and say 100. I think it'll take it. Nope, too many. And then let's take a look at the computation. So notice now it went down. So the cost is gauged by the lower number. So the lower cost is better. Therefore, what we're going to find is that there's an inverse ratio between the bandwidth and the cost. The higher the bandwidth, the lower the cost. The lower the bandwidth, the higher the cost. Because the lower bandwidth is going to be a value that we're not going to want to be able to use. But the problem is here is I mean, from 2 to 19 isn't that big of a deal with regard to the delineation, with regard to granularity. So what we want to do is modify this. Let's come in here and say spanning tree. And what we're going to do is I'm going to point out the value here, which is going to be path cost. So what I'll do is I'll type path cost. And then I'm going to pick a method. And the method I want to use is long. Now, long is going to allow me to utilize 32-bit values for my computations. So obviously, my numbers are going to get bigger. So when I come in here now and do show spanning tree for VLAN 1, what I'm going to find is now notice my values have a huge disparity between them. Now the reason this happens is using the old math, a 10 gigabit and a 1 gigabit, after I think 1 gig everything becomes 1. And you can't delineate between the two. And then with data center out there, what ends up happening is this becomes a major issue for us. All switches in the topology need to be configured to use the same in order to work correctly, yes. I'm just basically illustrating the method to alternate. There is, when you go in through your labs, you're going to find out that when you make changes to spanning tree, you need to make it on all of the devices participating in the domain, 9 times out of 10. But you guys wanted me to cover, or William wanted me to cover, the cost method long computation. So when we look at this, I'm going to go ahead and remove this because I don't want to actually have that running in here. So I'm going to say no spanning tree path cost method long. And the other thing that I want to also look at here is a command that gets a lot of neglect. It's a command that a lot of people don't use, and it's going to be spanning tree summary. And the reason that I like this command is that this command gives us a list of my VLANs. It lets me know whether or not I'm blocking for anywhere, whether or not I'm active in spanning tree for these, how many interfaces that I have that are actually forwarding, lets me know about my listening and learning states and things like that, and gives me the total number of computational VLANs that I have. But the other thing that I really love about this command is it tells me what's happening. Notice it tells me whether or not I'm using features we haven't talked about yet, like backbone fast, whether or not I'm using uplink fast. Also, it tells me how my computation is running. So whether or not I'm using the cost method long or the cost method short. Also, the other element that it tells me is it tells me what mode of spanning tree I'm running. So with one command, I can get a 30,000 foot snapshot of my entire layer 2 domain. Now, we've talked about TCNs, we've talked about change configurations, we've talked about spanning tree, but one of the huge issues that we have is the fact that, let's see, a question from William, do they go over internal VLAN association and switches? No. It's not in the context of version 5. Now, the problem with this is spanning tree is a pig. It's slow. It shuts down links. We'll deal with how to get around the whole shutting down links issue very shortly. But the main thing that I want you guys to understand here is that spanning tree is a pig. It just barely does what we want it to do. I mean, I remember back when telephones, and I have a bunch of clients that that were doing Linux, and the Windows machines or the Linux computers were booting up faster than the network could converge. And when they would try to authenticate using Samba to their drives and stuff like that, it would actually be blocked because the port wasn't in a state to be able to receive the information. And what we want to do is we want to actually deal with that. Now let's see here. Got a question from John. Do we use the port cost for the election of the root port right? Yes. It's used based on the shortest path computation to the root. And let me illustrate that, because this is another command that's pretty interesting. So right now, let me double check and see who's root for what. So spanning tree VLAN 10 and VLAN 1. All right, we're the root here. So what I'm going to do is I'm going to jump back over to cat 1. I'm going to make it the root for everything. So I'm going to say spanning tree for VLAN 124094. See what happens when you try to hit 96? I'm going to say priority 0. Notice it's going to bark at me. So I can't use 96. I can't use 95. I can only use 124094. And what we'll see is it's going to take it. Now I should be show spanning tree VLAN for all of, I should be the root for all of my VLANs. So I'm the root for 1. I am the root for 10. So now we've got all this going for us. Now, when we start looking at how we're going to be doing this, the computation is the fastest. How do we know how to get to the root bridge? Well, what I'm going to do is I'm going to cut over to cat 2, which is adjacent connected. And what I'm going to do is I'm going to say show spanning tree and just hit enter. This is going to tell me whether or not I've got my configuration. And I'm only running VLAN 1 here because I haven't created that VLAN. That's why I came over here. What I want to do is I'm going to actually take a look at and see how I'm interconnected to my other devices. So one of the things that we want to look at is the computation. We need to discover why spanning tree made the decision that it made, because we've got multiple links. Now what I'm going to do is I'm going to shut down some of these links. I'm going to shut down everything, show CDP, neighbors. I'm going to shut down everything that's not directly connected to cat 1. So in this instance, basically I'm just going to be shutting down 19 and 20. So config T, interface range, FAO 0, 19 to 20. Shut. Now this is going to leave me 3 interfaces. Now of the interfaces that I have, one of them is a gigabit Ethernet interface. So let's see what's going on. So now if I show interface trunk, I've only got one VLAN, VLAN 1, and I'm trunking across 23 and 24 because those are the only interfaces that I'm running trunking configuration in a mode that it's going to negotiate. We left the gigabit Ethernet out of the mix, and that's fine right now. But what I want you to see here is that if I come over here to cat 1 or cat 2, show spanning tree for VLAN 1, what I'm going to see here is that I have this interface, gigabit 0, that is the root bridge. I mean, it's the root port. Let's go over to cat 1 and take a look at this. Show, show, spanning tree, VLAN 1. gigabit. Now, the interesting component here is, notice it tells me that my spanning tree enabled protocol is IEEE. Now, when I had VLAN 2, when I had VLAN 10, notice it still said spanning tree protocol IEEE. Now, I thought I said that Cisco devices don't speak 802.1d, which is IEEE spanning tree protocol. They don't. They speak PVST and PVST plus. We can see that here by typing the do show spanning tree VLAN, spanning tree summary. PVST. That's the mode we're operating in. What that's looking at here is that we have backwards compatibility. So I can actually connect PVST plus to a common spanning tree instance and have it operate. In other words, I could have that router running in spanning tree and I can have PVST plus running on my switch and be perfectly fine because I am backwards compatible. How am I backwards compatible? Well, I get a priority value of whatever my priority value is. 32,768 plus 10 gave me 78, so it's 32,778. My switch would be 32,768. That's going to be the lower, so the router would end up being the root of the bridge. That's the problem. That's what you need to understand is that when we have backwards compatibility to CST, we're always going to default to where the CST instance is going to be the root bridge because what's going to happen is it's going to have the lowest priority. 9 times out of 10, depending on how we've got our system configured. Obviously, we can override it, but I'm talking about when we use everything at the default priority. Now, PVST plus is backwards compatible. We're going to find out all of the other instances of spanning tree that we're going to talk about are also backwards compatible. Now, looking at this backwards compatibility, the further we go and the more options that we integrate into our system and the more we accept industry standard norms, what we're going to find is that it becomes a little bit more problematic. So in per VLAN spanning tree, we're going to have instances where we have problems. And the thing that you're going to find out is that the newer our switches are, the more enhanced features that we're going to have currently running in our devices. And of enhanced features, the ones that I want to talk about specifically are going to relate to optimizations for PVST. So Cisco wised up. They said, well, PVST is a great idea. We love this VLAN thing. We love this 124.0.94. And the industry standards body is still saying, that's just whack, man. We don't want to, there's no way we want to be able to embrace that. So what we need to understand is that when we look at our interconnections, say for instance I have Cat 1 connected to Cat 2, connected to Cat 3, I'm going to have multiple links. And what we're going to look at here is the fact that, let's say this is the root bridge for all VLANs. Let's just say 124.0.94. Now, when we go in and we start looking at the optimizations here, here's the issue. The moment I come up here and say, well, I'm going to connect a port to a host, which is just a computer. Now, the problem is that this thinks, by default, PVST thinks that every one of these ports are going to be participating with another switch. So when we look at it, what we need to recognize here is that it's going to do the 15 learning, the 15 seconds, listening and the 15 seconds learning, which means it's going to block this port for 30 seconds. And like I said, in the early days, this became a problem because the machine came up long before the port would be able to operate. So what Cisco did is they came up with a concept called port fast. Port fast does this. We still go through listening and learning. I don't care what anybody tells you. But we forward through the whole process. So in other words, I don't have to wait the 30 seconds when I bring my port up and operational or during a recomputation. So now this host is able to send information just as slick as you please, absolutely no problem, everything's going to be working great and wonderful. Now the other thing that we need to understand is that when we start looking at how this configuration is made, on these ports, let's just arbitrarily pick some numbers. We'll say, this one is 23, this one is 24, 23, 24. We'll just say this is 19 and 20. These are the port numbers that we have. Now, like I said, spanning tree is also going to come in here and it's going to make a decision because we do not want traffic to be able to come into Cat3 and go back out the same link going back to the direction that it came in. So what we're going to do is we are going to prevent that from happening by allowing spanning tree to begin blocking ports. Now, interestingly enough, the port that's going to get blocked is the port that's going to have the highest number. So if I had 3 ports here, 19, 20, and 21, 21 would be blocked, 19 would be allowed to forward. Now, we've talked about spanning tree. Now, the problem here is that we've already run these computations. So I've got my ports that are blocked. What happens if I lose port 23 on the connection between Cat 1 and Cat 2? Well, what happens is I have to reconverge. I have to recompute how I'm going to create or how I'm going to get information from Cat 1 to Cat 2, which means my layer 2 domain is going to reconverge. Now, Cisco said, well, that's all well and good, but we don't want to wait that 30 seconds. So what they did is on this particular portion of the scenario, they created a concept called uplink fast. Uplink fast means that the moment this one goes down, I'm going to immediately go to this one, and I'm going to be operational. Now, this has to be configured on both ends of a configured link in order to have things work. Now, we also, in this scenario, notice we have 3 different ways to get to Cat 3. Now, we're only forwarding across one of them, but from the point of view of Cat 1, what if we lose one of these links? That means our layer 2 topology is going to reconverge. So what we are going to find here is that we're also going to have another feature that Cisco created called backbone fast. Backbone fast allows an indirect link failure to be optimized with regard to reconvergence on devices upstream or downstream from where we are in order to be able to reach the root bridge. So of the technologies we have are port fast, uplink fast, and backbone fast. Now here's the issue. All right, what I want to do is I'm going to go in here and I want to configure Cat 1 such that Cat 1 is going to be connected to a host. We'll pick a host, we'll find one in the system, and I'm going to enable port fast. So what I'm going to do is I'm going to bring up my devices, and we'll pick Cat 1. Let's see what we're connected to. I'm going to go to, I think it's R1. Let's see what, in config T, host name, R1, no IP, domain, lookup, line, console 0, logging, synchronous, no exec, timeout, exit, do write. All right. Now, I've got my device. My device is now configured. I'm going to go to interface, gigabit 00, no shut. Interface gigabit 01, no shut. Show IP interface brief is going to show me my interfaces. Notice right now I've got my embedded service module, which I'm not worried about. Here's the 2 interfaces that I'm worried about, and they are configured and they are up and up. So looking at this, that means I have a configuration, but I have no IP addresses assigned. That's the beauty of CDP. CDP is not going to look for any type of addressing. It just needs layer 2 interconnectivity. So what I'm going to do right now is I'm going to say do show CDP neighbors. And there it is. I'm connected to R1 via interface FA01 to interface FA01 on R1. So this is my local interface, and this is the interface that I'm connected to on the other end. Notice it even comes up here and gives me information. It tells me I'm connected to a 1921. Tells me that I'm capable for the ideas of router, for source route bridging, for switching, and for the I here, which is going to be IGMP connectivity. IGMP is the multicast routing protocol that we run on hosts to devices that they're connected to. PIM is going to be the protocol we run between routers and stuff. So looking at this, we can see we can get a lot of information. But what I want to do is I'm going to go to interface FA01, and I'm going to say spanning tree port fast. And I'm going to hit enter. Now we're going to get a lot of information. I'll take my head out of the way so that we can walk through it. Notice it says port fast should only be enabled on ports connected to a single host. Connecting hubs, concentrators, switches, and bridges. To this interface when port fast is enabled may cause temporary bridging loops. This is referred to as an interim loop or sometimes called a convergence loop. That's what we're trying to avoid. Now the idea here is that port fast has been configured on this interface, and it will only take effect when the interface is in a non-trunking mode. Now notice show interface FAO1 switch port. Notice my modes. My mode is still dynamic auto. Notice I am a static access, that's my operational mode. But should I receive a BPDU and try to form a link, what's going to end up happening is I have the capability of bringing it up because it is in mode negotiation of trunking on. All right, now looking at this, what I'm going to do is I want to go back over to R1. Now what I'm going to do is I'm going to have R1, actually let me see something here. I always forget this command, bear with me. Show interface, show spanning tree. Show spanning tree. Thought it was under interface, but it's not. It is. Interface. G or FAO1 port fast. Notice it's enabled. That command is one of those commands that just bugs the crap out of me because it really only gives you one other thing. Manuel's suggesting using the detail. So if I do show spanning tree interface FAO1 and use the detail command, it's going to give me a whole lot of information associated with it. This is my favorite command, by the way, when it comes to computation and determining why decisions are being made in our topology. And that's what I want to talk about before we dive into the labs. All right, now looking at this, when we go in and we start setting the configurations up and we're working here, what I want to do is I want to demonstrate the fact that my port fast configuration is enabled. Now what I'm going to do is I'm going to go to R1, and again I'm going to use bridging. I'm going to say bridge 1 protocol IEEE. Show spanning tree. We're now participating in spanning tree. Well, do show spanning tree. We're now participating in spanning tree. Now what I want to be able to do is I'm going to go to the interface, G01, and I'm going to say bridge group 1 on this interface. I'm just going to hit enter. Now just for good measure, I'm going to go GIO01, because sometimes this hangs. I haven't really tested it on these devices, on the 2900s. Shut. Give it time to compute that it's been turned down, then bring it back up. And what we're going to do is we're going to back over here to Cat1. And what I want to do is I want to notice that it went down, came back up. That was because I shut the link down. But I'm going to redo the command of port fast. And notice what happened it's disabled. Now when we look at this, I can come up here now and execute the show command that was shared with us. I think it was Manuel that shared it with us. And what we're going to see here is notice I have received BPDU 0. But if I repeat this command, notice now I received a BPDU. The moment I received the BPDU, I took the port out of port fast. So the moment that BPDU came from R1 through gigabit 01, GI1, arrived on FAO 01 on Cat1, that BPDU came through, and the moment that BPDU came through, spanning tree took that BPDU, recognized it, and removed my port fast config. Now the problem here is now I've got an issue, because let's see what happens on my refresh. Still just to have received the 1, and that was all I needed. But the problem now is notice, I'm still sending BPDUs. So I'm trying to communicate with this device. Now the reason I'm communicating with this device is this is Cat1, so I'm the root bridge. In a per VLAN spanning tree plus and in a common instance spanning tree 802.1d deployment, after convergence, it's the root bridge and only the root bridge that's responsible for sending BPDUs, unless there's been a reconvergence issue. And even then, it's the only one that's going to send authoritative BPDUs. But the main object of this exercise now is that we are no longer operating in spanning tree. Now what I'm going to do is I'm going to go over to Cat 1. I'm going to take that off. I'm going to say no bridge group 1. And then I'm going to come over here to Cat 1, and we should see port fast come back up. Let's see what happens. I may have to shut the interface down. Really don't want to force it to reset, but I will. Go back over to Cat 1 after I made the change. Sometimes the process just hangs. So we'll come up here and we'll say shut, no shut. Always wait till you receive the messages that your interfaces have gone down before you bring them back up, because sometimes we have a tendency to shut them down and bring them back up faster than the process has to recognize that they went down, and what happens is things kind of hang. So here, notice, enabled. So we're good to go, and the process is now back up. But the issue here is this doesn't really stop anything. This doesn't stop us from saying, okay, I want to stop this individual port, because what could end up happening, I mean, William, he's smart. He's going to go out, he can go out onto eBay, buy a switch, unplug his computer at the office and plug in a switch, and he's going to have the capability of being able to partake in the layer 2 environment, provided it's designed the way it currently is designed. In fact, he could even become the root bridge because of the simple fact that we didn't change the manipulation concepts. So the issue here is I'm going to go back over to Cat 1, R1, and what I want to do is I'm going to reapply this. Bridge group 1, shut, wait for the messages, no shut, bring it back up. Let's take a look at our do show spanning tree. Okay, notice I'm participating on port 4 now. I'm in listening state. Designated root priority is 1. Designated bridge priority is 1. Got all kinds of information I'm learning about my neighbor. Let's see if we can get it out of here. And let's see what we've got. We're still learning. So we've gone through listening and learning. Still learning. Want to make sure the port comes up. Now we're forwarding. Now what I want to do is I want to take a look at my configuration here. Notice that my MAC address is 5E80, last 4. Now let's cut over to Cat 1 and see what Cat 1 says now. So show spanning tree VLAN 1. Okay, VLAN 1, 5E80, that matches. So in this scenario, Cat 1 is the root bridge. Now the problem is, like I said, we're sending and receiving those BPDUs. Now, one of the things that I could possibly do is I could come into my system and I could make some configurational changes. I could say, we've talked about uplink fast, we've talked about backbone fast, we've talked about port fast. We are talking about port fast. So now what I want to do is I want to stop William from messing with my network. So I have an option, I have a number of options to be able to do it. The safest is going to be the concept of BPDU guard. Now what I'm going to do is I'm going to come in here and I'm going to say interface. Actually, I'll do it here. I'll do it globally first. I'm going to say spanning tree, port fast, default. So what's going to happen now is any interface that I have that's not participating in trunking is going to automatically be running port fast. In fact, what I can do is I can cut over here to interface FAO1, and I'm going to take off the individual command that I have here. I'm going to say no spanning tree port fast. But I want to repeat the command using the port fast output. Notice it says it's still enabled. Even though I come up here and say show run interface FAO1, we're going to see that I have no additional config. If I pick another interface, let's say 13. No spanning tree info allowed. Why? Because the port is down. So if I come over here and go to interface FAO, well, it's not forwarding, so it's not going to make a difference. If it was up and running, you would see that it would be running in port fast mode. Now, here's the scenario. Am I still receiving those BPDUs? Show, man oh man. All over the map today, guys, sorry. Show interface, FAO1, or show spanning tree. Interface, FAO1, detail. All right, so, well, I've received one. Doesn't look like I've received any others. Now, the reason I haven't received, why haven't I gotten another BPDU from R1? R1 sent me one BPDU. Anybody have any idea why I've not received any BPDUs from R1? Because I'm the root bridge. I received one BPDU, which I used to calculate the election. Cat 1 has become the root bridge, and now what ends up happening is by virtue of the fact in PVST Plus and in 802.1d, Cat 1 is the root bridge. It's not going to be sending, Cat 1 is the only device that's going to be sending BPDUs in a normal scenario. So let's cut over to R1. All right, so when we go through here, one of my options would have been, under the interface, I could type bridge group 1, and what I can do is you're going to notice I'm going to have the capability of disabling spanning tree. Again, this is not in the context of the actual lab, but what I wanted to be able to do is I wanted to be able to specify things like priorities. So when I come in, notice I have priority command. So what I'm going to do is I'm going to say priority 0. And let's see what happens. So I'm going to cut back over to R1, Cat 1 I mean, and take a look at my spanning tree now. Show spanning tree for VLAN 1. Well, we're still the root bridge. This bridge is the root. Take a look at 10. Are we still the root for it? This bridge is the root. Let's take a look at our computation. Our priority here is 0. So the change, now what's happening is the MAC address is now becoming an issue, or still an issue. So let me see if I can force this. What I'm going to do is I'm going to say config T. I'm going to say spanning tree VLAN 124094, and I'm going to say priority 4098. Exit. Now let's execute it and see what happens for VLAN 1. Notice we're still the root bridge. Now also notice we have edge mode operations. So on 1, on 11, and on 14, 1, 11, and 14. Now edge, that's the system's way of telling us that we're running port fast. Now looking at this, what should be happening here? Let's take a look. So I've got a priority of 4097. I go to R1, show spanning tree. And what's my priority here? My bridge identifier, my priority is 32768. So we've got port priority of 0. We've got port path cost. But I thought that I said that I wanted the port to run, show, run interface, G01. I wanted it to be a priority of 0. Let's take a look at that command again. Config T, interface, G01, bridge group 1. And let's look at what the priority says here. What's the option? So we've got priority, that's the interface priority. So when we go in and we start looking at this, let's take a look and see what we have. See, can I execute a spanning tree command on the global configuration of a router? Sure can. Let's see what else I have the capability of doing. Well, see, now notice I have R1. I'm saying VLAN. So let's say VLAN 1, priority, and I'm going to pick a priority. Let's say 0. So, I mean, this is on a router. Why can I execute spanning trees on a router? Because I'm running my bridge. I'm actually operating as a switch or a bridge, a few ports that are operating for it, actually only one. Now let's see if that changes the scenario. Do show spanning tree VLAN 1. And notice it's still got us as the root port. So let's go over to R1 and see if we can't trump this selection, because we're not sending BPDUs. So config T, interface, G01, shut. No shut. Do show spanning tree. Link is up now. We're listening. If it doesn't force, I'm waiting for it to exit listening state. Wanted to go to forwarding state. And then what we're going to do is we're going to look at the BPDUs. So learning. From learning, we'll go to forwarding. We just got to wait 15 seconds, which seems like forever. The bridge group number and the VLAN number don't have to match. What I can have is I can have multiple instances of bridging groups on the same device. So pretend like it's breaking it up into virtual bridges. So now we're forwarding. Port priority 0. I didn't really want to mess with that. I should have took that back out. Current route priority is 4097. And there's why. The bridge identifier priority is not being changed, but that's not a problem. What I wanted to do is I was trying to force it from the reverse end. I want to watch the fact that my values here are going to increment. So I'm receiving BPDUs from the root. That's really all I wanted to do. I was just going to reverse the process and show it on the Cat1 switch. But in fact, I'm going to receive these every 2 seconds. So as you can see, they're incrementing. So in this instance, we can see it's the root bridge that's responsible for sending the BPDUs after convergence. Now, what I want to do is I want to make a modification to Cat1, and then I'll give you guys a break, I promise. On Cat1, what I'm going to do is I'm going to enable another command. I'm going to say config t, and I'm going to say spanning tree, and I'm going to specify BPD, port fast, BPDU guard default. So that means on any interface that's operating in port fast, I'm going to immediately turn BPDU guard on. Now the issue is now, if I receive a BPDU on this interface, I'm going to alter its behavior. So first, show spanning tree, interface, FA01. Let's see what we got here, BPDU. Do I want to use the detail command? And let's take a look and see what we've got. First of all, are we even operating in port fast? It's disabled. It's disabled because we received a BPDU. But notice it hasn't brought anything down. Why? Because my network is reconverged. So what I need to be able to do is, in order to experiment with this BPDU guard feature, I'm changing the behavior. So right now we saw, or previously we saw that if I received a BPDU, all I did was took my port out of port fast state. Now what I want to be able to do is I want to put it into a state called BPDU guard disabled. So the moment I receive a BPDU guard, I want to bring that interface down. Now the only way that I can do that, force it, is to go back over to R1, and I'm going to shut that interface down and then re-enable it. And then it should actually stimulate it to send a BPDU. So shut. I'm going to type no shut. It didn't take, Jeffrey. That's one of the reasons that routers, we don't do a lot of bridging on routers anymore, because when we set it up, I mean, Cisco still wants to have this concept of VLAN, but really and truly what we're doing is we're picking what VLAN we're going to operate using the native VLAN config. But bear in mind, when we create a router on a stick configuration, the switches are going to recognize the VLAN traffic, because what we're going to do is we're going to hard code the encapsulation. Yeah, on a switch, on a router, when we're running bridging, it doesn't know anything about VLANs. That's the whole benefit of having it set up as common instance spanning tree. Now, Cisco's since then hacked that process. So right now I'm going to no shut it, which is going to force the sending of the BPDU. And notice what happened here is I brought it back up. Line protocol on the interface changed to up. Let's go back over to Cat1 and see what's going on now. So show spanning tree port fast. It's still enabled. Are we even receiving a BPDU now? Doesn't look like we are. G01. Oh, I'm going to get rid of that. There we go. Now here's the issue. Spanning tree detected a BPDU guard incursion. It was received on FA01, and then the guard was enabled, and the port was actually disabled. So if I come in here and I show interface, one of my options in here is going to be able to show status. So let's look at the status of our interfaces. Right now we see FA01 is disabled. Now the problem with disabling this port is if I want to bring that port back up, I got to do it. So I've kept William from using his switch to play with my network, but I've made more work for myself. Now when we go through here, it was saying error disabled, but let's take a look at the actual rationale here. So let's see, show spanning tree. No. Show, bear with me just one second. Show, trying to remember the command. Show interface. It is showing up as show spanning tree VLAN 1. One's not in the list. Nope. It's down. You're right, it is error disabled. Show interface status. Show. Notice right here, error disabled, but the reason is BPDU guard. Now the thing is if I shut it down and bring it back on, what's going to end up happening is it's going to reset itself, and the error is not going to be reinstated until I go over to R1 and send another BPDU. All right, so the main thing that we're going to notice here is I want it to be in the state of BPDU guard error disabled. Now, what I want to illustrate here is, like I said, I'm making work for myself. So one of the options that I could have is I could actually come in here and I could create an error recovery process. So I could type error disable recovery. And then what I can do is I can specify the cause, and I can say specifically what the cause is. Notice right here I have BPDU guard right there in my listing. So if I come up here and say BPDU guard, hit enter. Now what I'm going to do is I've created an error recovery process for any interfaces that have encountered an error recovery issue with association specifically to BPDU guard. I could have just as easily used all. Now I also can come in here and say error disable recovery interval, which is going to be how often do I want to reset this thing. So if it goes down, how long do I wait to reset it? I'm going to say 30 seconds. I'm going to hit enter. Now what we're going to do is we're going to wait 30 seconds. And what will happen here is on or around 30 seconds, I don't think I've disabled any type of time synchronization here with regard to the process. We should see this interface come back up. Now the question is will it go back down? It all depends on whether or not we receive another BPDU. Now, what I recommend to a lot of people specifically is the fact that when we set this up, you give it enough time to where it's going to be uncomfortable for the person that's causing this problem, especially if you warn them. But what we also want to do is ensure that it comes up before we get in trouble. So as you can see right now, I'll take myself off the equation. It says attempting to recover from a BPDU guard state. Notice it changed the interface port back to up. And then what we'll do is we'll just repeat that show command where we look at the status error disabled, and we'll see that we have no interfaces. Show interface FA01. And we should see everything that's going. So I wanted to look at not the state, but the detail again. There it is. And now notice we've received no BPDU since the port came up. Now obviously I could go over to R1, shut it, no shut it, waiting for the message to come up. And the moment it comes back up, what will end up happening is Cat1 should detect the BPDU. The moment it receives the BPDU, it's going to take the interface down. Now the benefit here is that what it's going to do is it's going to reset that interface in the background after it waits for another 30 seconds.